Good afternoon, students, and welcome to the online class on elasticity, engineering physics subject. So today we will discuss further uh, part of the elasticity. Before we go to the next part of the elasticity, we will just do the recapitulation of the things what you have done in the previous class. Before that, I would like to request all the students to join the class on time. Okay, though it's not compulsion, you may feel it, but joining the class on time is very important, and it maintains discipline, self-discipline for yourself. Okay, so we cannot help you in if you come late. Okay, but it's a type of self-discipline that you have imposed on yourself. It will help you in the future life that it should be on time. You should enter the class on time. You should go to lab on time. You should go to work on time. You should do the things on your time. Okay, so these are the basics. If you start learning now, so after 4 years uh, you will be having a very good attitude towards the time management. Otherwise, no, it will have a lot of issues in your career. Not here in college, and other thing will make up all the things, lost things. But when you go to career, doing some job, okay, there no these things may play very important. Joining late to the meeting, like coming late to the class. Okay, these are all bad habits. Okay, over the time they only grow exponentially, they will not decrease. So I request you to join on time. Okay, thank you. And I told you to collect your um, login ID. Still then you are not collected. Okay, that is also shows the your negative attitude towards the things. Okay, that should not be done. So you have to collect it. So there's a lot of having a lot of advantages of that. Okay, so I shall just do a recapitulation of the things. So before that, I will share the screen. Okay, hope you are seeing this screen, students. Hello.
Yes, sir.
Okay, thank you. So, so in the last class, no, so we'll discuss what are the things we have done in the last class. Okay, so we have studied this stress versus strain graph. Oh, it's here. So in the last class, we have studied the stress versus strain graph. So this is a graph which represents the stress along y-axis and strain along the x-axis. Basically, we study how the strain is changing, how the strain is varying when you apply a stress. That means when you apply a force, how the deformation takes place in a body, that is understood with the help of this stress strain curve which is on your screen. Okay, so actually it is having two main regions, plastic region and elastic region. Okay, so this is how we are splitting the curve, stress versus strain curve. Okay, so when the stress is very small, okay, when the stress is small, that is the force applied is small, the body will regain its original shape and size after removing the applied force. So I had given you an example of a wire. So this is a wire. This is the original shape of the wire, like this is the original shape. And if I apply a force, this is the force that I have applied. How I applied the force? By applying a mass. Okay, or you can apply it physically. So this is the force I have applied. So you can see the force. So once I apply the force in this direction, there is an elongation in the wire. The elongation is X. Okay, the original length is L. Okay, so by application of the force, there is an elongation. If you remove the force, removing the force means you make the force equal to 0. Okay, so this is the force equal to 0. Once you make the force 0, the elongated wire goes back to its original shape. This is the original shape and length. It goes back to the original shape. This is the way the original length is, provided you make the force 0. That means I have made the stress 0. So keep in mind, when you remove the stress, or when you remove the stress, the body starts to regain its original shape. Now look here, this is the extended shape. What I have done, I have removed the force. So when I remove the force, it starts to gain its original size and shape. Decreasing the stress means decreasing the force what you have applied to the wire. Okay, by decreasing the force, the body goes back to its original shape. Okay, so this is the idea that should be kept in mind. More the stress, more the deformation, more the change in dimension, more the value of x. You are getting the point. If you apply more force, more the stress. Stress is more. What about the displacement x? X will also be more. Now what do I do? I go on decreasing the stress. Now I am decreasing the force. Once I decrease the force, it goes back to the original state. So keeping that in mind, what happens when you apply a force which is less than a certain limit? Okay, say this point P, up to the point P, if you apply the stress. So this is the point that you have. Up to this point, if you apply the stress, the body will gain the original shape and size. Okay, so this point P is called as proportional limit. It is called as the proportional limit. So point zero, from origin to point P, the body is in a linear state. So from here to point P, the body is in a linear state. That is, stress is directly proportional to strain in that region. So there the body will gain its original shape, okay, and size if you remove the applied stress, because stress applied is very small. So this is the amount of stress that you have applied. So I will take this as the small term. I will just take it as K. So I will take this as K. If the stress is less than the value of K, this is the proportional limit. We call it as the proportional limit. Okay. So if it is less than the proportional limit, it is going to go back to its original state. Therefore, the Hooke's law is obeyed very well between the case. Now look here, Hooke's law is obeyed very well. So it is obeying the Hooke's law. It is followed perfectly well. So the stress is removed. The path is same. Whatever the path it takes to go from O to P, okay, when the stress is removed, it will come back with the same path. Okay, then beyond P up to Q, beyond P up to Q. So from P to Q, this region. So this is the region from P to Q, this region. What happens? The stress is not proportional to stress. That means strain is not proportional to stress, or stress is not proportional to strain. Okay, it is a non-linear region. So PQ is a non-linear region. This is beyond P and up to Q. So this is a beyond P and up to Q. This is the region. So beyond P up to Q, the body doesn't follow the Hooke's law. Hooke's law means stress is directly proportional to strain. This is not followed by the curve. Okay. So here, though it is an elastic material, if the stress is beyond the uh, uh, proportional limit, it is in the elastic mode, but it is not satisfying the Hooke's law. That means in this region between P and Q, so in this region between P and Q, it is not following the Hooke's law. It is not following the Hooke's law. Okay, got it. So in this region, it is a non-linear part. Okay, but still it is a elastic material, but some plasticity has come into its picture. Okay, so that is called as the non-linear phase, and the point Q is called as the elastic limit. This is the elastic limit. Okay, point Q is called as the elastic limit. That means this is the maximum stress. It is called as sigma U. Look here. Okay, this is the maximum stress. You can see here. So this is sigma U. So beyond sigma U, if you apply any of the stress, the material enters into the elastic region. So this is called as an elastic limit, or in other words, it's called as the yield point. Y, sigma Y is called as the yield point. Keep in mind, if the stress is greater than the yield point, it enters into the plastic region. Now, once once it enters into the plastic region beyond Q and S, so this is in the plastic region. So if the stress is, if the whatever the stress that you apply, if it is greater than the point sigma U, rho sigma Y, that is the yield point, what happens? It enters into the plastic region. This is the plastic region. You can see here. This is the plastic region up to the point X. Okay, from Q up to point S, it is in the plastic region. That means it is in the deformed shape always. Okay, so if you increase the stress, the deformation is increasing more and more. Okay, now up to point Q, what happens here? If the stress is up to point Q, up to this limit, okay, the curve will follow the same path. OP, okay, what happens? The curve will follow the same path. That means as the stress increases, the curve will increase from O to P, from P to Q. But what about Q to P, Q to S? Of course, it is going to increase from Q to S, but when it is coming back, so it is going to increase like this, okay, from Q to S. But what happens when you decrease the stress? When you decrease the stress, the curve will not follow the same path like this. It is not going to follow the same path like this. It is not follow the same path. It is going to follow different path. So what happens if the stress is removed? For example, at point R, if you are decreasing the stress, the curve will not trace the actual path it has taken. It is going to take some other path. It takes the path RC. This is the dotted line. You can see here. This is the curve it is going to take like this. It is the curve it is going to take. So up to this point, okay, it is going to decrease like this. So this is the way it is going to decrease. Okay. So what happens here? Once it is decreasing in this manner, when the stress is completely removed, look at this point. When the stress is completely removed, our stress is completely made zero, our force is made zero. The strain is not completely zero. There is some amount of strain that is still existing, OC. So that means I have removed the force. After removing the force, if you look at the above diagram, the body should go back to its original state like this. Should be in a original state, but it is not in the original state. It is in the deformed state. Therefore, OC represents some residual strain. That means residual strain means it is having some deformation left over when I still remove the applied stress. So this is called as the permanent set. OC is called as permanent set, or it is also called as residual strain, OC, or it is also called as deformation that is existing. Okay. Now, after that, if you still increase the stress up to the point X, so this is the point X, you can look here. This is the point X. So this is called as ultimate strain. That means the stress is very, very high at the point X. Okay, this value is called as sigma U. So this is called as ultimate strength. Okay. So what happens beyond this value, if the stress whatever you have applied is beyond this value of ultimate strength, okay, the body will start to break down. That means it starts to get damaged. That is the point. Okay, up to point X, if you increase the stress, it is in a state where it is in some ideal, in some good condition. But if the stress is beyond the point X, what happens? The body starts to deteriorate. So once the wire, if you have the wire, if you apply the stress, what is the stress that you have applied? Okay, it is beyond the value of ultimate stress, that is ultimate strength, that is sigma U. If it is greater than sigma U, the wire that you have here, okay, this is the wire you have. So this wire starts to thin. Okay, it is going to thin. Okay, thin means its diameter goes on decreasing. Okay, if the stress is more. So at a particular, so the wire is thinned in such a way that the material starts to loosen its strength, and after that slowly the material gets deteriorated. And if the stress is such that if the value of the stress is at the point S, the wire completely break down. Okay, so at that point we call it as a fracture point. That point is called as the fracture point. So this is the way the stress versus strain curve varies for a what you call the wire. Okay, very simple thing. You have to remember 2 points. Between O to P, it is a linear region, obeys Hooke's law. P to Q region, it is non-linear region, where the material is an elastic material, but it is not obeying the Hooke's law. Beyond Q up to point S, it is a plastic region. Okay, if you remove the stress when you apply the stress in the plastic region, it is not following the same path. it is following the path OC, where along the path RC, where some amount of stress is still left over. That OC is called as a permanent set or permanent deformation. Okay. At point X is called as an ultimate strength, where it is handling maximum stress. Beyond that, it is not handling any stress. It breaks down. So point S, if the stress is at the point S value, it breaks up. Why? Because beyond the point X, the wire starts to deteriorate. Deteriorate ಅಂದ್ರೆ ಹಾಳಾಕೊಂತ ಬರ್ತದೆ ಜಾಸ್ತಿ ಸ್ಟ್ರೆಸ್ ಹಾಕಿದ್ರೆ. So this is the curve what you have. Okay. So this is the very important question for your IA. Explain the stress and strain curve. Okay. With this, we shall go for the next part. Before we go for the next part, we shall solve few problems on this. Okay. What we have left in the last section. Okay. So let us go for the problematic part that we have left over. Okay. So this is the next one. Take down the problem. Okay. Calculate the extension produced in a wire of length 2 meter. Of length 2 meter and a radius of 0.013 meters due to a force of 14.7 Newton applied along its length. Given the Young's modulus of the material is Y equal to 2.11 into 10 to the power of 11 Newton per meter square. This is the case. Okay, take down this, and if you can try to solve this. Okay. Hello, students. Solve this problem and
Yes,
tell me the answer. Okay. So you take down this, just students, do one thing. You can take down this and solve it as an assignment. So I would like to go for some other important discussion. Okay. Because in the next class, if I do it, it will be half and it's not possible for me to start a new point, new chapter in the next class. So you take down this as an assignment and solve. Else I will solve at the end. Don't worry. You take this as an assignment and solve. Okay. Solve this as an assignment and solve. Okay. Okay, students, are you there?
yes, sir. Yes, sir.
Adirla, idnu ನೀವು ಬರ್ಕೋರಿ. Can solve it afterwards. Okay. So we shall go for the next one. Okay. There's other important terms that you should know here. Okay. 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 There are some other terms that you should know. Okay. So there are some other terminologies or terms that are used in elasticity again and again. Okay. Okay. So which characterizes the physical property, which characterizes the elastic property, which characterizes the elastic property. Okay. There are many other property. There are many. Okay. Not one, many properties. There are few other terms. Okay, that you should know. The first term that you should know is the longitudinal strain coefficient. Longitudinal strain coefficient. I have a certain wire. So what is this longitudinal strain coefficient? Let us go for that understanding. I have a wire. So the wire is in the shape of a circular manner. Okay, so I have a wire. Okay. So this wire is like this. This is the wire. This is too much. Okay. So this is a circular wire. Okay. And this is the cross sectional area. Okay. Got it. So this is the cross sectional area of a wire whose length is L. This is the length of the wire. Okay. Whose length is L. Okay. This is the length of the wire. So what I do, I apply a force. Okay. I just apply a force. Once I apply a force, there is an extension in the wire. Okay. So this is the extension in the wire like this. Okay. The wire gets elongated. Let us assume that this is the elongation that has taken place. How much is the elongation? The elongation is X. The elongation is X. So here I can define strain. So what type of strain it is? Here by the application of the force. Okay, I have applied a force here. It is along the length. Keep in mind this is the wire. The wire is applied with the force such that it is along the length of the material, length of the wire. So therefore I can define the stress for this. So if I define a stress, now since it is along the wire, therefore I should call it as a longitudinal, sorry, first I will define strain, then I'll go for the, first I will apply the force. Once I apply the force, there is an extension in the value of the wire. So this much is the extension X. So this is the longitudinal, okay, or linear strain. This is the first one, strain. Okay. What is the ratio of what is strain? Strain is the thing, but the ratio of change in dimension to the original dimension. What is change in dimension? Change in dimension is the value of X. This much has the dimension that is changed. What is L? Original length. So where L is the original length. Okay. And X is the change in dimension. Change in length. Length is increased. Okay. Change in length. So this is how I define the longitudinal strain. Okay. Now I can also define stress. What is stress? Stress is nothing but force per unit area. This is the applied force. What is the area? This is the cross-sectional area A. This is the area A. So I can write stress is equal to F by A. Now here, what type of stress it is? The stress is such that there is an increase in the length. You keep in mind, increase in the length of the wire. So whenever the stress is such that it is increasing the length, therefore that stress I should call it as the tensile stress. It is called as the tensile stress. You're getting the point. It is known as the tensile stress. Okay. Now here our tensile stress are also called as longitudinal stress. In general, it is also called as longitudinal stress. It is also called as longitudinal stress. Now this is stress, I will take it as T. Okay, longitudinal stress. Keep in mind, I have taken it as T, not the tension. It's not a tension, it is a longitudinal stress T, that is equal to what is stress? Stress is given by F by A. F by A. So this is the equation number 1 and this is equation number 2. Then I can define longitudinal strain coefficient. What is this longitudinal strain coefficient? Okay, therefore I can define a longitudinal strain coefficient. Very important term. Okay, we will use it this one again and again in the coming classes. Okay, longitudinal strain coefficient. What is this longitudinal strain coefficient? So it is the thing, but it's the longitudinal strain is defined as the longitudinal longitudinal strain produced per unit stress per unit stress applied. So this is the meaning of longitudinal strain coefficient. How is it defined? It is defined as the longitudinal strain produced per unit stress. Okay. Now you have been, just for your reference, I will write here, you are defining the modulus as stress divided by strain. So this is nothing but stress per unit strain. Now I am defining the longitudinal strain coefficient alpha exactly inverse of this, Therefore, if I rewrite this in terms of the ratio, so I can write it as longitudinal strain coefficient, So this is alpha. Look at how it is defined. It is a longitudinal strain produced per unit stress. It is the longitudinal strain per unit stress. So it is the ratio of longitudinal strain per unit stress. Okay, per longitudinal stress. Okay, simply this is the way we can write it. Okay, so therefore I can write the value of alpha like this: stress by strain by stress. So it is just inverse of the modulus value. Therefore alpha equal to, what is a strain? Strain is given from equation 1 and 2. So therefore from 1 and 2 I can write. So strain, longitudinal strain is given by X by L. Now longitudinal stress, this is okay from 1 and 2. Okay, from equations 1 and 2 I can write alpha. Look here, this is the X by L is the longitudinal strain. This is how I define strain. What is stress? Stress is nothing but T. So I will take the stress as T. So this is longitudinal stress. I can take this as the T. Okay, I can write it like this. So this is how I can define the value of alpha. Now keep in mind here I am again writing where T is the longitudinal stress. It is not the tension. Don't be confused with the tension. Okay, tension is also represented by T, but I will write it as T as the longitudinal stress. Okay, got it. Now here X, or I can still write it as R alpha is equal to X divided by LT. How the R I can write X is equal to alpha LT. What is this X? Anybody can tell me what is this X? What is X?
Extension, sir.
Very good. What is X? X is the extension. You can see here. What is X? X is the extension. You can look here. Okay, where X stands for the extension that has taken place. So you can calculate the value of X. Okay, what is X? So here X is the extension, where X is the extension or elongation. Extension or it is a thing but the elongation in the length of the wire. You can calculate it. Okay, we'll take this as 3, this as 4. Very important. You can calculate how much is the value of extension. You can calculate how much. If you know, if we can calculate x, okay, we can calculate x. X can be calculated. X can be calculated if we know what we know. If we know alpha, what we should know? Alpha. What is alpha? Alpha is the longitudinal strain coefficient. Longitudinal strain coefficient. Okay. It is also called as. Alpha is also called as strain or longitudinal strain. It is also called as the. Keep in mind, it's also called as longitudinal strain per unit stress. Per unit stress. That means per unit stress, how much is the strain that is taking place? That is the meaning of alpha. ನೀವು ಒಂದು unit stress ಹಾಕಿದ್ರ, okay, what if you put 1 unit of stress, what is the corresponding strain? That strain is called as the alpha. That is called as the alpha. For the applied unit stress, okay, this is the applied stress, 1 unit stress. Okay, it may be 1 Newton per meter square, or 1 Newton per centimeter square, whatever it may be. So 1 unit stress will produce some strain. So what is that strain? That is called as alpha. Then you should know the original length of the wire. You should know the T. What is T? T is the longitudinal stress. If you know all these values, you can calculate the value of X. How much is the extension that can be produced in the wire? You are getting the point? So this is the very important point that you will get it. Okay. So go for the next one. This is alpha. Okay. Hope you have taken down. Then next one, that is called as the lateral strain coefficient. This is the second term that you should know. Okay.
Sir,
Students are here.
Sir, want your screen?
Okay.
Wait, sir.
ಆಯ್ತಾಯ್ತು ಇಲ್ಲ ಸಾರಿ ನಾನು ಅದನ್ನ ಜೂಮ್ ಮಾಡಕತ್ತಿದ್ದೆ ಇಲ್ಲಿ ತೊಂದರೆ ಇಲ್ಲ just a minute okay now it's clear okay
Yes sir.
ಆಯ್ತಾ ಬರ್ಕೊಂಡ್ರಾ
Yes sir.
Okay fine, let's go for the one more important term that is called as the lateral strain coefficient. Lateral strain coefficient. Lateral this is called as beta. Okay, so I'll explain this first, then define it. So I have a wire, same wire as you have seen the last part. Okay, I have the wire in the form of a circular in shape. This is the wire which is in a circular shape. This is the wire. Okay. Got it. So I will just have to make this bit larger this time. Okay, I will make bit larger so that it is clear for you. Okay, I have a wire which is in circular manner. So this is the in circular manner. So therefore this will be the cross section here. Okay, this is the cross section that you have for the wire. Okay. Now what is the length? Length is L. This is the length of the wire. What is the length? Length is L. Now what I do, I apply the force. You've done it many times. Once you apply the force, there is an elongation in the wire. So this is the elongation. There is an increase in the length of the wire. So this much is the increase in the length of the, I will take this as X. Okay. This is the length of the wire. Now I will ask one simple question to you. Now, if you are applying a force, if you by applying a force, there is an increase in the length of the wire. Now, the point is, where does the material comes for to have this much of increase in the wire? You are getting the point. Only this is the material I have. This is the material you have. This much is the length of the wire. Okay. By applying the force, there is an extension in the length of the wire. What is the extension? It is X. Udda Tandra, you are adding some wire to it, some material to it. So this X means you are adding some material to it. Do you agree with this? Adding some material. How the? So increasing the length means you are adding some material to the wire. Is it physically possible that you are adding some material to the wire? ಸಾಧ್ಯ ಐತಾ ನಿಮ್ ವೈರ್ಗೆ ನೀವು ಮಾಸ್ ಹಾಕಿದಾಗ ಉದ್ದ ಆಗುತ್ತಾ ಹೌದಾ? There is an increase in the length. Simple question. If the length is increasing, okay, where does the material comes for the wire? Material ಬೇಕಾ ಉದ್ದ ಆಗಕ್ಕೆ ಹೌದಲ್ಲ? ಉದ್ದ ಆಗ್ಬೇಕಂದ್ರೆ ಬಟ್ ಉದ್ದ ಆಗ್ಬೇಕಂದ್ರೆ ಹೆಂಗ ತನ್ನಷ್ಟು ತಾನ ಉದ್ದ ಆಗುತ್ತಾನ ಅರ್ಬಿ ಇಲ್ಲ. You have to bring some piece of cloth, attach it and you have to stitch it, then it becomes lengthier. Now here I have a wire, a metallic wire. I have applied a force. Once I apply a force, there is an increase in the length of the wire. Okay, there is a increase in the length of the wire, X. Now the question is, where does the material comes from? Okay, you are adding some material. Increase in length means length is increasing. That means adding some material to the wire. Are you really adding the material? The question is that, are you really adding the material? Are you really adding? No, we are not really adding some material. There is some other phenomenon that is taking place. Okay, let us see what is that phenomenon. Okay, so we are adding some material to the wire. Okay, how are we really adding to it? Let us see what is the phenomenon behind it. Okay, now once you apply the force, there is an increase in the length of the wire. Okay, so this is the direction of the force. Okay, I will write it here again for simplicity. So this will be the direction of the applied force. This is the cross sectional area A. Okay, this is the cross sectional area. Now what happens is that when you apply a force, okay, by it may be physical force or it may be a load, by applying a load M, there is an increasing the length of the wire because some of the material gets displaced in the wire. Some of the molecules or the atom gets displaced and they come and add up to this region. They add up to this region. So what happens actually happens here is that by applying the force, there is a decrease in the diameter of the wire. Keep in mind. So this much is the increase in the length. So therefore here I will write. So the length is increased in this case. Okay, there is a increase in length. Increase in length of the wire. Okay, so this is because, okay, I can say that this is due to the, it leads to because it leads to decrease in the diameter, of the wire. Diameter of the wire. You are getting the point? Now I had asked one simple question. How the material is added here? How the material is added? Okay, the material is not added by hand. Actually what happens is that once you apply a force, okay, there is an increase in the length of the wire because the diameter, whatever the diameter you have, let us assume that the diameter of this wire is D. Let us assume the diameter be the D for the wire. By application of the wire, the length increases by X, but the diameter D decreases. The diameter shrinks. Therefore, actually, the diameter shrinks and it is going to decrease like this. This is the way it is going to happen. So the blue line you can see there. Okay, this is the one which you have. Okay, so I have the wire. Okay, so it has shrunk in diameter. Diameter nagathre sum agtade. So there is a decrease in the diameter. Got it? So therefore, whatever the decrease in diameter that has taken place, keep in mind. So this is the decrease in diameter. Okay, so look at the diameter. Earlier the diameter was D. Now the diameter is, what is the diameter? It is lesser than the previous one. It is lesser than the previous one. Okay, so what is the diameter now? The diameter is D dash. Now the diameter decreases. Therefore, here on application of the force, therefore the stress that is present, stress decreases the diameter. The diameter decreases. Okay, what is the diameter? Diameter was D. Okay, decreases to new diameter. What is the new diameter of the wire? The new diameter is D dash. You are getting the point. The wire has been thinned. So if you have seen the rubber that is used in a sweet box, I have given an example. No, this is a box. Okay, and you are having the wire, the rubber like this. So this is how the rubber works. It is perfectly fitting the box. Is it not? It's perfectly fitting the box. Got it? So since it is perfectly fitting, we are using it. Now, if I pull it, the same rubber, okay, it is going to have an extension of varilla. This is the, so this size rubber gets extended like this. Okay, if it is extending like this, means if the dimensions are increasing like this, are we adding material? Are we adding material to the rubber? No, we are not adding any material, but still there is an increase in the length of, in the diameter of the rubber. If you look at this rubber, the diameter of this rubber is decreased. So this is the diameter D of the wire of the rubber in rest position when the force is not applied. When I apply the force, it gets elongated. At the same time, the diameter of this rubber becomes D dash, which is lesser than the original diameter of the rubber. ಸೊ ಏನಾಗುತ್ತೆ, ಆ ರಬ್ಬರ್ ಜಗ್ಗದಾಗ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಆ ರಬ್ಬರ್ದ ಡಯಾಮೀಟರ್ ಏನಾಗುತ್ತೆ, ಕಡಿಮೆ ಆಗುತ್ತೆ. ಹಿಂಗಾಗಿ ಆ ಮಟೀರಿಯಲ್ ಉದ್ದ ಹಾಕೊಂತ ಹೋಗ್ತದೆ. ಅದರಂಗ ಇಲ್ಲಿ ವೈರ್, ಇಲ್ಲಿ ನೋಡ್ರಿ, ಈ ವೈರ್ ಏನಿತ್ತಲ್ಲ, ನಾವು ವೈರ್ ಫೋರ್ಸ್ ಹಾಕಿದಾಗ, ವಿಚ್ ಫೋರ್ಸ್ ಐ ಆಮ್ ಅಪ್ಲೈಯಿಂಗ್? I am applying this force. So once I apply a force, the diameter which was D, this was the diameter, it gets shrink to D dash. The diameter ಏನಾಗತ್ತೆ ರೀ, D dash ಆಗಿ shrink ಆಗ್ತದೆ. So ನೀವು ಫೋರ್ಸ್ ಅಪ್ಲೈ ಮಾಡೋದು longitudinal force, along the length you are applying the force. Therefore there is an increase in the length because there is a decrease in the diameter of the wire. Keep in mind. Okay, so therefore this is also a type of strain. This is also a type of strain. Therefore I can write the diameter decrease, the stress, this stress decreases the diameter of wire to new diameter D dash. Therefore I can write the change in diameter, the change in diameter. How much is the change in diameter of the wire? If I write, that will be equal to D. This is the change in diameter. It's not the new diameter. New diameter is D dash. Original diameter is D. Change in diameter is D equal to, small d is equal to capital D minus the new diameter d dash. This is the way I have to write the value of the change in diameter. So change in diameter means change in dimension. It is the change in diameter. Dimension is changed. Which dimension? Diameter. Now I can define stress for this. What I can do? I can define first one strain. Then I will define stress. So I can define strain. How you define strain? Strain is defined as the change in dimension. Change in dimension. Ha, ಹೇಳ್ರಿ.
Sir, screen ಕಾಣತಿಲ್ಲ sir.
ನಾ ಶೇರ್ ಮಾಡ್ತೇನೆ ಒಂದ ಮಿನಿಟ್. Change in dimension to the original dimension. Original dimension. Okay, ಒಂದ ಮಿನಿಟ್ ರೀ. Okay. ಆಯ್ತು. Okay. So ನಾವು ಫೋರ್ಸ್ ಅಪ್ಲೈ ಮಾಡೋದ್ರಿಂದ ವೈರ್ ಲೆಂತ್ ಇನ್ಕ್ರೀಸ್ ಆಯ್ತು, ಆದ್ರೆ ಡಯಾಮೀಟರ್ ಏನಾಗುತ್ತೆ? ಡಿಕ್ರೀಸ್ ಆಗ್ತದೆ. ಓಕೆ, ಆಯ್ತಾ? ಸ್ಟ್ರೇನ್ ಹೆಂಗ್ ಡಿಫೈನ್ ಮಾಡ್ತೀರಿ? ಸ್ಟ್ರೇನ್ ಅಂತಂದ್ರೆ it is nothing but change in dimension to the original dimension. This is the ratio of change in dimension to the original dimension. What is the dimension that is changed? It is the diameter that has been changed. Okay, here it is the diameter. Okay, what is the dimension? Is the diameter. So therefore I can write strain is equal to, it is strain is equal to, okay, change in dimension. What is the change in dimension? It is the diameter. Keep in mind, what is the dimension? I have to mark, it is the diameter. What is the change in dimension? It's the change in dimension is diameter. So I have to take this as d. So strain is equal to, okay, I have to take it as small d divided by the original dimension. This is the original dimension. So I will write it neatly here. Original dimension. Original dimension. Okay, what is original dimension? Original dimension, original diameter. What is the original diameter? Original diameter is d. Okay, you can look here, the one with the black ink. So that is the original diameter. Ha, ಬರ್ಕೊಂತೀನಿ, ಕೊಡ್ತೀನಿ.
ಅಲ್ಲ ಸರ್, ಸರ್ ನೀವು ಈಗ ಬರೋದ ಕಾಣತಿಲ್ಲ ಸರ್ ನನಗ.
ಹೌದು, ಯಾರು ಕಾಣವಲ್ದ? ಅತಾಡಿ ಹೋಲ್ಡ್ ಮಾಡಿ.
ಕಾಣಿಸ್ತಾ ಇದೆ ಸರ್.
ವಿಸಿಬಲ್ ಸರ್.
ವಿಸಿಬಲ್ ಐತಾ? ಹಾ, ಆಯ್ತು ನೋಡ್ರಿ. ಹಾ, ಆಯ್ತು.
ಸರ್ ನನಗೆ ಕಾಣತಿಲ್ಲ ಸರ್.
ಅಲ್ವಾ, ನಿಂದ ನೆಟ್ವರ್ಕ್ ಪ್ರಾಬ್ಲಮ್ ಇರ್ಬೇಕಲ್ಲ, ಬ್ಯಾರೆದವ್ರು ಹೌದಿಲ್ಲ? ಬ್ಯಾರೆದವ್ರು ಕಾಣ್ಲಿಕ್ಕತ್ತೇನಪ್ಪ? ಹಾ ಹಾ, ಲಕ್ಷ್ಮಿ, ಆಮೇಲೆ ಲಕ್ಷ್ಮಿನ ಚೈತ್ರನ ಅವ್ರು ಮಾತಾಡ್ರು.
ಲಕ್ಷ್ಮಿ ಸರ್.
ಹಾ, ಆಯ್ತು. ಲಕ್ಷ್ಮಿ, ಸ್ವಲ್ಪ ನೀವು ಸಿಗ್ನಲ್ ಬಿಟ್ಟು ಹೊರಗೆ ಬರ್ರಿ, ಅವ್ರ ಮನಿ ಬಿಟ್ಟು ಹೊರಗೆ ಬರ್ರಿ, ಸಿಗ್ತೈತಿ ನೆಟ್ವರ್ಕ್. ಸೊ ಚೇಂಜ್ ಇನ್ ಡೈಮೆನ್ಷನ್. ಚೇಂಜ್ ಇನ್ ಡೈಮೆನ್ಷನ್ ಅಂದ್ರೆ ಯಾವುದು? ಡಿ. ಎಷ್ಟು ಚೇಂಜ್ ಆತ ಡಯಾಮೀಟರ್? ಮೊದ್ಲಾಕಿಂದ ಡಯಾಮೀಟರ್ ಡಿ ಅದ. ಫಸ್ಟ್ ಡಯಾಮೀಟರ್, ಒರಿಜಿನಲ್ ಡಯಾಮೀಟರ್ ಇಸ್ ಡಿ. ಓಕೆ, okay, this is the original diameter. Okay, new diameter after the stress is applied. How that? So therefore change in diameter is d minus d dash. Okay, so that I can take it as small d. Here it is written d minus d dash is the small d, and original diameter I will take it as d. Now here this strain is not just simply called as strain, it is called as lateral strain. It is called as the lateral strain. It is called as the lateral strain. Now bare strain annangilla ಏನಂತೇವೆ ಅದಕ್ಕೆ? Lateral strain. Lateral strain ಅಂತೇವೆ. ಏನಂತ ನಾವ್ರಿ? We will call it as lateral. Okay, now this lateral strain, okay, whatever you get here, this I will call it as equation number 1. Okay, this lateral strain, okay, is perpendicular to the applied stress, to the applied stress. Okay, ಇಲ್ಲಿ ನೋಡ್ರಿ, ಇದು ಫೋರ್ಸ್ F ಅದನ, ಏರಿಯಾ A ಅದ. So the direction of the stress is like this along the force. E direction ದೊಳಗೆ stress ಅದ. But the decrease in diameter is along the x direction. If I take this as x direction, if I take this as y direction, the decrease in diameter is along the x direction, negative x. Therefore, the change in diameter is along x direction. Therefore, change in diameter means it is nothing but the strain. Therefore, strain is lateral strain. Keep in mind, lateral strain is perpendicular is perpendicular to the applied stress. Okay. Now, therefore, it is called as lateral strain d by d. Now, after that, I can write the stress. Okay, which type of stress? Okay, it's a normal stress I can write. Okay, it is longitudinal stress only. So I can write the value of stress as, okay, the stress is given by, okay, how to write the stress? So this is the stress what you have. You can also write it as longitudinal stress, longitudinal, or I can write as tensile stress. So I can write this stress as T equal to force per unit area. This is called as the force per unit area. This is the force that you have. Area is the cross sectional area. Therefore, stress T is equal to F by A. Okay, this I will take it as 2. Okay. Now, I can define the term lateral strain coefficient beta. Okay, I can define the lateral strain coefficient beta as is defined as, I can write it as is defined as in the same way as we have done in the last part. Okay, how to define it? It is the lateral strain. I can write it as it is the defined as the defined as the defined as defined as the lateral strain produced lateral strain produced per unit stress applied. Okay, so it is just similar to the one what we have done in the previous case. Longitudinal strain by longitudinal stress. You have this equation, no, alpha strain by stress. Second one is also same thing. It is the ratio of strain by stress. Therefore, I can write here lateral, or I can write the same thing, lateral strain coefficient, okay, equal to beta. This I can write, it is the ratio of lateral strain divided by, it is not, look here, per unit stress. Therefore, per unit stress that is applied, per unit stress. Which type stress? It is maybe applied stress, or it may be longitudinal stress. Okay, I'll just write it as applied stress. Okay, per unit stress applied. So from equation 1 and 2 I can write, therefore, okay, from 1 and 2 as we have done in the last part, from 1 and 2, equation 1 and 2. So this is also called as lateral strain coefficient beta. Okay, this can be written as beta, can be written as, okay. So what is lateral strain? It is d by d. I can write it as lateral strain coefficient beta is equal to lateral strain is small d by capital D. Applied stress, this is nothing but the tensile stress what I have. This is nothing but the applied stress. This is T. This is the lateral strain equation number 1, and this is equation number 2. Okay, so therefore I can write stress instead of stress is equal to F by A, I will take F stress is equal to T. I will just take it as T. Okay, so this is the value for beta. Okay, lateral strain coefficient. Okay, so beta, therefore beta is equal to, this I will take it as 3. So beta is equal to d by d, or I can write it as d divided by capital D into d, therefore dt. Therefore I want d is equal to beta d into t. So this I will take it as 4. So what is this 4 giving? What does this 4 tells you? 4 tells you that the d is actually the this is the value of d. So this d is nothing but change in the dimension of the wire, change in dimension of the wire, that is change in the dimension of the diameter. How much diameter is changed? Okay, so this is the D. What does this D stands for? Therefore, D stands for the change in, change means what's here? It's particular decrease in the diameter of a wire, diameter of wire. Okay, this is the value of D. How much is the decrease in the diameter of a wire when you apply the force? You take a wire, you apply the force F. There is an increase in the length of the wire. This is the increase in the length of the wire by X. Okay, this is the X that has increased. So once the length is increased, the diameter D shrinks to D dash. It is going to decrease from D to D dash. Therefore, the change in the diameter is D equal to D minus D dash. Therefore, strain by stress applied, lateral strain by applied stress. That is, lateral strain is D by capital D and stress is T. Therefore, I get the decrease in diameter. How much decrease that is taking per unit stress? That is called as the D. You have the decrease. If you know, if you can calculate how much is the decrease in diameter. If you know beta, what you should know? If you know beta, what is beta? It is the lateral strain coefficient. D is the diameter, original diameter. T is the stress that is applied. So it is lateral strain coefficient. Strain coefficient. D is the original diameter. Okay, T is the applied stress. If you know this value, I can easily calculate the value of the D. How much is that decrease in diameter? And at last, there is one important term that is called as the Poisson's ratio. It's called as the Poisson's ratio. Okay, we'll finish it off. This one, Poisson's ratio. Very important term. Okay, Poisson's ratio. Okay. Okay. It is given by sigma. Okay. What is this Poisson's ratio? So this Poisson's ratio, okay, is defined as like this. Within elastic limit, within elastic, you can directly write also. There's no necessary like this. So within elastic limit of a material, of a body, within elastic limit of a body, okay, the ratio of, keep in mind, the ratio of lateral strain, the ratio of lateral strain to the longitudinal strain, lateral strain to the longitudinal strain is constant. Is constant. I will not call it as is constant. Okay, and is called, and that constant is called, okay, this is a constant, and that constant is called Poisson's ratio, and is called Poisson's ratio. This is sigma, okay, ratio. Okay, it's called as Poisson's ratio. Now read it again. What is this? Within elastic limit, the ratio of what? Lateral strain to the longitudinal strain. Lateral strain to the longitudinal strain is a constant. If I take the ratio, which ratio? Now that is, if I take the ratio of what? Lateral strain. Okay. So lateral strain to the longitudinal strain. If I take this value for a wire, okay, if you look at this diagram, from the first one I can find, this is the one I have. This is the one I have. This is the lateral strain. I have alpha. Okay, this is alpha. You can see here. This represents the lateral strain, and this represents the beta. Beta represents the lateral strain, and alpha represents the longitudinal strain coefficient, and alpha represents the lateral strain coefficient. Now here I can find what is lateral strain. The first case I have written here, what is longitudinal strain. Here it's the length now, therefore I can take the longitudinal strain. It's here x by L. It is x by L, longitudinal strain. Lateral strain is, it's here, lateral strain is, it's here, equation number 1 you can see here, it is d by d. So the ratios of these two, so therefore I can take the ratio that is equal to lateral strain, it is nothing but d by d, change in diameter to the original diameter. Longitudinal strain is change in length to the original length. If you take this, this is actually a constant. It is actually a constant. It gives you a constant. So therefore, here it is b by d. Okay. It gives you a constant. Okay. So this constant is called as the Poisson's ratio. This is called as the Poisson's ratio. Okay. Or I can still write it as lateral strain by longitudinal strain, longitudinal strain. I can rearrange it like this. Okay, look here, d by d. Okay, I will divide this by t, the stress. X by L, I will divide the numerator and denominator by t. So this is on dividing numerator and denominator by stress that is applied. What is the stress that is applied? T. NR means numerator, DR means denominator. Just in shortcut I have written like this. So here this is a constant, keep in mind. Now look at this b by dt. D by dt, this numerator, this is nothing but beta. If you look at this equation, no, if you look at that equation for beta, beta is given by d by capital D divided by t. Okay, lateral strain divided by applied stress. Therefore, this can be written as, okay, this can be written as, okay, this can be written as, okay, beta, and this can be denominator. This is the denominator. This denominator x by L divided by t. I have missed it here. It's divided by t. So the x by L divided by t. This can be written as alpha. If you look at this one, this alpha, it's here x by L by t. Beta. What is beta? D by d by t. Okay, so if I rearrange it for this equation, then the ratio, what is the ratio? It is ratio of lateral strain to longitudinal strain. It is the ratio of lateral strain to longitudinal strain is nothing but beta by alpha, that is equal to a constant. It will be a constant. It is a constant. This constant sigma is called as, the sigma is called as Poisson's ratio. It's called as the Poisson's ratio. Okay, this is the way I can define like this. Okay, or I can define the Poisson's ratio as R. Very important, this one, Poisson's ratio definition. We will use it again and again. Poisson's ratio is defined as it is defined like this. It's the ratio of, keep in mind, lateral strain to, this is beta. Now keep in mind, here you have beta, no? So this is beta, this is alpha. Beta stands for lateral strain coefficient. Lateral strain coefficient. Beta, the ratio of lateral strain coefficient beta to longitudinal strain alpha. strain coefficient alpha is a constant. It is a constant called as Poisson's ratio. It's called as the Poisson's ratio. Okay. Directly you can also write it. Okay. So what is the ratio? Poisson's ratio. So Poisson's ratio is nothing but the ratio of lateral strain coefficient by longitudinal strain coefficient. Okay, this is beta and this is alpha. Okay, so beta by alpha. Okay, so this term we are using it again and again in the coming classes. Why? Because there are a lot of derivations that we are using. Okay, so it is beta by alpha. Poisson's ratio. Okay, so hope it is clear to you. Okay, Poisson's ratio. Okay, so I shall stop here itself. In the next class, very important, don't miss that class. Why? Because there are relations in the next class. What we'll do is we'll derive the relations, very important relations between Y. What is Y? Young's modulus. Neta, that is a bulk rigidity modulus, or I will write as K bulk modulus, and neta, the bulk modulus. Young's modulus, bulk modulus, and modulus of rigidity. These three are the independent elastic moduli. We can connect them using some relation. So we are using the relations. Okay. So we'll build some relations. So these relations are very, simple but confusing. Therefore, you have to be there in the next class. We will use all these concepts, whatever we have used, no, here alpha, beta, then how to calculate this D, how to calculate this L, X extension. So we will use it and we will derive it in the next class. Okay, very important. Don't miss that class. I shall stop here itself. In the next class, we shall continue. Okay, I request all the students to come on time. Otherwise, I have to keep on taking the classes extra and extra. Okay, got it. So I shall stop here itself. In the next class, we shall meet. Okay. So before you leave, I think attendance is very low, 27. You ask your friends to attend the class. Okay, very important derivation. The next class. Okay, thank you. You can leave the class.
Thank you, sir.
Thank you.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.